In this, the first of the benzene videos, what we're going to do is take a look at the structure of benzene and how it was derived. So one of the first things that we're going to do is, using some percentage composition by mass, work out what the formula of benzene is. So benzene was isolated for the first time in 1825, and upon analysis it was found to contain 92.3% carbon and 7.7% hydrogen. Can you work out an empirical formula? So pause the video now and see if you can work out the empirical formula. So we'd set up an empirical formula calculation like this. We'd put the percentages by mass, and we're going to convert those masses into moles, and to convert mass to moles we need to divide by AR. So check that you got the right answer for the number of moles. There you go. And then we're going to divide by the smallest one so that we can work out what the ratio is. And so both of these numbers are basically 7.7, so the ratio is 1 to 1. And that gives us an empirical formula of CH. So once you have the empirical formula, you can work out the molecular formula. You need to add up the empirical formula mass. So use your calculator, add up the empirical formula mass. And you should have got 13. Now it tells us that the relative molecular mass is 78. So how many 13s fit into 78? So on your calculator, work out how many 13s fit into 78. You should get the answer 6. And therefore you can give the molecular formula. And so it was discovered that the formula of this new compound was C6H6. Now it took quite a long time for somebody to come up with a feasible structure for C6H6. How could 6 carbons only have 6 hydrogens? And it was Kekule who was the first person to convince us of a structure for this new molecule benzene. And what did Kekule's structure look like? Well, Kekule's structure was a ring of the 6 carbons, and each one of those 6 carbons had one of the 6 hydrogens, like that. And then in order to satisfy the bonding, there were alternate double and single bonds. And this was Kekule's structure for benzene. Pause the video and see if you can draw that in skeletal formula. So there we go, it's a hexagon with double bonds in it, 3 double bonds, alternating single and double. Now if Kekule had been right, so was Kekule right? If he had been right, there'd be some things we would be able to say. If we've got these carbon-carbon double bonds, one of the things we would expect is that if we were to add bromine water, it would be decolorized. Now we know that double bonds are a little bit shorter than single bonds, so if this was correct, then this would not be a regular hexagon with all sides the same length. There would be different size bonds. So this would be another bit of information. So what we're going to have a look at now is further scientific evidence that was gathered that proved that this structure couldn't quite be correct. So piece of evidence number 1 is when they added bromine water to benzene, it didn't get decolorized. Therefore it cannot contain carbon-carbon double bonds. That's our first piece of evidence. Okay, so carbon-carbon double bonds do cause bromine water to be decolorized, but benzene does not. Therefore benzene cannot contain carbon-carbon double bonds. So evidence piece number 1, if you're asked in an exam, is that it does not decolorize bromine water. What's our second piece of evidence? Well, it relates to those bond lengths. So like we said, if they were double bonds and then single bonds, we'd have an irregular hexagon because double bonds are shorter than single bonds. But actually when we do an X-ray model of benzene, we see that all the bonds are the same length. So that's our second piece of evidence. So all the bond lengths of carbon-carbon bonds in benzene, all the bonds are the same length. Now that is our second piece. Not all the bonds, not the carbon-hydrogen bonds, but all the carbon-carbon bonds are the same length. And what we notice is that they're actually longer than a double bond normally is, but shorter than a single bond normally is. So they're somewhere in between. We say they're intermediate in length between a double and a single bond. So that's our second piece of evidence if the exam board asks you to prove Kekule's structure wrong. And the third piece of evidence is to do with thermochemical data for hydrogenation of benzene. Now that is a bit of a mouthful, but it has to be correct in the exam. Thermochemical means the enthalpy changes, so enthalpy change data for the reaction that is adding hydrogen for hydrogenation of benzene suggests that it's more stable than Kekule's structure. So the data tells us that benzene is more stable than it should be. So let's have a look at that. So if we have a look at this reaction, the hydrogenation, so hydrogenation means adding hydrogen. If we were to add hydrogen to cyclohexene, like that, so we take our cyclohexene structure and we add hydrogen, we'd get cyclohexane. And when we do that, and we measure the enthalpy change, what we find is that it is minus 120 kilojoules per mole for that reaction. So, if we were then to look at doing that to Kekule's structure, which sometimes in exams, because we're trying to disprove this structure, is called the hypothetical cyclohexa 1,3,5 triene, which would be another name for what we're, it's not actually there in existence, it's a hypothetical. It's what Kekule thought benzene was. Turns out it's not, so it's not real, it's hypothetical. And it is a cyclohexane ring with triene, 3 enes at 1, 3 and 5. What do we think that would be? So let's have a look at that reaction. So if we were to take a look at that reaction, what we'd be doing is we'd be hydrogenating. We'd need to add 3 lots of hydrogen because Kekule's structure has 3 double bonds. This is cyclohexa 1,3,5 triene. Okay. What would you think the value for the enthalpy change would be? So if 1 double bond is minus 120, 2 double bonds would be minus 240, then 3 double bonds should surely be minus 360. This is not an actual thing because it's hypothetical. This would be our expected value for benzene. So then what actually happens is when they hydrogenate benzene, and the structure we're going to be using for benzene as we move through the course is to draw a hexagon, but to put a ring in to represent something called the pi bond. If we do the same reaction to our actual benzene, then what we'll see is that the enthalpy change is not minus 360, the enthalpy change is minus 208. And this is our actual value. So our actual value is less negative than our expected value, and that is because benzene is more stable than Kekule's structure proposes. So we're going to have a look at how we know that it's more stable now on an enthalpy profile diagram. You just need to be aware that the exam board don't expect you to know these numbers, they expect you to understand what these numbers represent, but not actually memorise these numbers. Okay, so let's have a look at that. So if we were to put the first of these enthalpy changes on, we can see that if we go from cyclohexene to cyclohexane, we released, so we went down minus 120 kilojoules of energy, so we went down 120. So where would we put Kekule's structure, that hypothetical cyclohexa 1,3,5 triene? Where would that be on our enthalpy profile diagram? Remember that the higher up this diagram we go, the more unstable we are. We've got more contained energy, so we're full of energy and we want to release it. We're not very stable. So where would we go if we were the hypothetical Kekule structure? See whether you can put that onto the diagram. So there we go. If we put that on, because there are 3 times as many double bonds, we'd expect to see this 3 times as high up, and the enthalpy change would be minus 360. So the size of the arrow, remember, represents the magnitude of the number, so 360 is 3 times bigger than 120, so the arrow is 3 times bigger, and the down is the minus. So where does real benzene, actual benzene structure go in comparison to Kekules and cyclohexene? See if you can put that onto the diagram. There we go, we've got the benzene structure at -208, and what we can see is that there is a stability here. There's a difference between this number and this number, and the difference in the size of those two arrows is 152 kilojoules per mole. So what we would say about that, if we were looking at that diagram, is the real structure of benzene is more stable. It's 152 kilojoules more stable than Kekule's structure. This is our third piece of evidence. The real structure is 152 kilojoules per mole more stable. It's lower in energy. It's got less pent-up energy. Okay. This difference is known as the delocalization energy. This difference in energy is due to something called delocalization. Something that we might write quite a bit in this topic is about benzene being more stable due to the delocalization of electrons in the pi bond, and that's going to become clear as we move through the next little section. So this is the end of our section on the structure of benzene. We've looked at where it came from, we've looked at what the formula is, we've looked at the first derived structure that Kekule came up with, and we've looked at the evidence that disproves Kekule's structure. In the next video we're going to have a look at the structure that is accepted currently for benzene.